What if I told you the definitive map of the universe, the one we've relied on for a generation, was fundamentally wrong? For decades, a single photograph defined the edge of everything we could see. It was a masterpiece, but it was also a keyhole. We were peering into a vast dark room and mistaking one tiny sliver of light for the whole story. Now, a new eye has opened, and it's revealing that the room is bigger, stranger, and was built far faster than we ever imagined. Let's explore this together. 10,000 galaxies. How do you take a picture of the beginning of time? In 2004, astronomers led by Stephen Beckwith gambled on a wild idea. They pointed the Hubble Space Telescope at a patch of sky in the constellation Fornax so dark and empty it seemed pointless. For 11 straight days, Hubble stared into that void, gathering photons that had traveled for over 13 billion years. When the images were stitched together, the result was legendary. The Hubble Ultra Deep Field. In an area less than 1/10 the size of the full moon, nearly 10,000 galaxies appeared. Each smudge of light was an entire system of stars, gas, and dust. Here were cosmic pinwheels, ancient glowing ellipticals, and messy distant blue clumps, hinting at the universe's chaotic adolescence. This image gave astronomers their first real census of the early cosmos, allowing them to count and categorize galaxies from different epochs. It confirmed that galaxies evolve, growing from smaller, more irregular shapes into the grand spirals we see today. This wasn't just a picture, it was a core sample of cosmic history, showing us what the universe looked like when it was just 800 million years old. For a generation, this single breathtaking image defined the boundary of our observable universe. Hubble's limits. But here's the thing about that legendary image, it was profoundly incomplete. Hubble, for all its power, has critical limitations. Its 2.4-meter mirror, while revolutionary, can only gather so much light. This means the faintest, most distant objects remain just beyond its grasp. More importantly, Hubble sees primarily invisible and ultraviolet light, but the universe's expansion stretches the light from the most ancient galaxies, shifting it far into the infrared spectrum, a phenomenon called redshift. This ancient light is simply invisible to Hubble. As the former director of the Space Telescope Science Institute, Robert Williams, who championed the original Deep Field project, knew, they were pushing the telescope to its absolute limits. Cosmic dust, thick clouds left over from early star formation, also blocked and scattered visible light, hiding entire populations of galaxies from view. And the field itself was a pencil-thin slice of the cosmos. Statistically speaking, it could have been an unusually empty or an unusually crowded neighborhood, and we'd have no way of knowing. It was deep, but incredibly narrow, giving us a glimpse of the early universe's richness, but no sense of the broader context. The Golden Mirror. To see what Hubble couldn't, you don't just need a bigger telescope, you need a different kind of eye. Enter the James Webb Space Telescope. At its heart is a breathtaking 6.5-meter primary mirror, nearly 3 times wider than Hubble's, and with more than 6 times the light-gathering area. This isn't just a larger mirror, it's an engineering marvel designed for a completely different purpose. Coated in a microscopically thin layer of gold, the 18 hexagonal segments are optimized to reflect infrared light with extreme efficiency. Led by senior project scientist and Nobel laureate John Mather, the team behind Webb didn't build a replacement for Hubble, they built a time machine. Its mission is to reach deep into the infrared, the realm where the light from the universe's first stars and galaxies now resides. The entire observatory is protected by a 5-layer sun shield the size of a tennis court, which keeps the mirror and its instruments at a frigid -233 degrees Celsius. This extreme cold is essential to prevent the telescope's own heat from blinding its sensitive infrared detectors. Webb was designed to see where Hubble goes blind, peering behind veils of cosmic dust and capturing ancient light that has been stretched by the expansion of space-time itself. This is the key to unlocking the universe's hidden chapters. Seeing the invisible. So, how does this golden giant actually pull back the curtain on the early universe? Well, the secret is in its instruments, which are tuned to the infrared. As space expands, light from the most distant galaxies gets stretched to longer and longer wavelengths, a process astronomers call redshift. The further back in time you look, the redder the light becomes. Hubble loses track of these ancient messengers, but Webb was built to follow them. Its near-infrared camera, or NIRCam, is sensitive enough to capture light from galaxies that formed when the universe was just a few hundred million years old. Its mid-infrared instrument, or MIRI, goes even further, piercing through the thick clouds of cosmic dust, that once blocked our view entirely. This technological leap was harnessed by teams like the one led by University of Texas astronomer Caitlin Casey, who envisioned a new kind of survey, one that captured both the depth to see the faintest galaxies and the breadth to understand their environment. These instruments don't just take pictures, they also perform spectroscopy, breaking light down into its constituent colors to measure a galaxy's distance, chemical composition, and motion. It's this combination of sensitivity and analytical power that transforms what was once missing data into a continuous cosmic history. Webb makes the invisible visible. 780,000 and counting. If Hubble's deep field was a single photograph, the Cosmos Webb survey is an entire atlas. Forget 10,000 galaxies. Over 250 hours, Webb's gaze swept across a region of the sky roughly the area of 3 full moons. Within this single continuous mosaic, astronomers have cataloged nearly 780,000 galaxies. Let that number sink in for a moment. That is not a statistical estimate. Each one is a real captured system. Co-led by Jehan Kartaltepe at the Rochester Institute of Technology, this survey is about 80 times larger in area than the Hubble Ultra Deep Field and achieves nearly the same depth. The sheer scale is staggering. The light from some of these systems began its journey when the universe was less than 300 million years old. Because of its size and depth, the survey isn't just finding more galaxies, it's finding entire populations that were completely invisible to Hubble. Red, dusty, massive galaxies that are now filling in the gaps in our understanding of cosmic history. This massive data set allows astronomers to move beyond studying rare, individual objects and start analyzing entire populations, providing the statistical power needed to test our cosmological models. This is not a random sample, it's a census on a cosmic scale. The Cosmic Web. When you map nearly 800,000 galaxies in one continuous sweep, you stop seeing individual points of light and start seeing the underlying architecture of the universe itself. For the first time, astronomers can trace the cosmic web in a single, unbroken field. We now see the grand tapestry of filaments, clusters, and vast empty voids that shape the destinies of galaxies. As pioneered by astronomers like Margaret Geller, mapping this structure reveals that galaxies aren't scattered randomly. Filaments act as cosmic highways, funneling gas and matter into dense intersections where galaxy clusters form. In these crowded neighborhoods, galaxies merge and interact violently, often triggering furious bursts of star formation or having their gas stripped away. In the vast dark spaces between, voids can stretch for millions of light years, leaving some galaxies to evolve in total isolation. This atlas view allows scientists to study how a galaxy's environment shapes its life. Graceful spiral galaxies tend to live in the quiet suburbs, while chaotic irregular galaxies are found in the dense, violent city centers of clusters. With this map, we can now directly observe how the cosmic web itself guides the flow of matter and dictates where and when galaxies are born and how they die. The cosmic web isn't just a backdrop, it's the landscape that dictates everything. The infinity anomaly. But this new map isn't just confirming what we expected on a grander scale. It's showing us things that, according to our current models, simply shouldn't exist. Across the Cosmos Webb field and other deep surveys, Webb is finding anomalies that challenge the very rules of cosmic evolution. For instance, a team led by researcher Hannah Ubler found a merger of two galaxies, a system called ZS7, just 740 million years after the Big Bang. Inside this collision, they found a supermassive black hole of 50 million solar masses that is growing far more rapidly than theories allow. Black holes this big, this early, defy the standard model where they are expected to grow slowly over billions of years. This discovery suggests that mergers are a critical pathway for black holes to grow at extreme rates in the early universe, or perhaps they form from massive seeds we don't yet understand. It implies the universe had a fast track for building these cosmic monsters that our theories haven't accounted for. This single system forces a radical rethink of the relationship between galaxy mergers and black hole assembly in the first billion years of cosmic time. The evidence is clear. The universe was building monsters long before we thought it was possible. Too fast, too early. It's not just the black holes that are breaking the rules, the galaxies themselves are maturing at an impossible rate. Theory predicted that the era around 1 to 3 billion years after the Big Bang, dubbed cosmic noon, should be filled with young, chaotic, star-bursting galaxies. Instead, Webb is finding giants that are already quenched. Their star formation has completely shut down. A team led by astrophysicist Adam Carnell identified a galaxy called GS9209 that had already built up 40 billion suns worth of stars, and then abruptly went quiet just over a billion years after the Big Bang. According to researchers like Carl Glazebrook, who has spent his career studying these systems, this is like finding a retiree in a cosmic nursery. Even more confounding, Webb is finding galaxies with well-ordered spiral arms and stable bars at redshifts, where we expected only turbulent, messy proto-galaxies. These structures require billions of years of calm, stable evolution to form, yet they exist in the chaotic early universe. This suggests the underlying dark matter halos that anchor galaxies grew and stabilized much faster than our simulations predict. The unmistakable implication is that the processes of galaxy formation and shutdown are far faster and more efficient than any of our models can explain. First light. So, just how far back can Webb see? The answer is rewriting the first chapter of the cosmic story. Webb has delivered spectroscopically confirmed record holders, with the current champion being JWST Z14-0. Its light began its journey to us just 290 million years after the Big Bang. For the astronomers on the JD's team, like Kevin Heinlein, who first spotted it, the moment was electric. This wasn't a faint hint, it was a clear, confirmed signal, but the biggest surprise wasn't its age. Using the ALMA observatory, another team led by Stefano Carniani detected the chemical signature of oxygen in this galaxy. Let me explain why that's so important. Oxygen isn't created in the Big Bang. It's forged in the hearts of massive stars and scattered through space when they die. Finding it in a galaxy this ancient means at least one full generation of massive, short-lived stars had already formed, died, and enriched their surroundings with heavy elements. This process, known as chemical enrichment, was thought to take much longer. The universe was building complexity at a breakneck pace, playing out its first cycles of birth, death, and recycling in record time. Rewriting the rules. When the data consistently contradicts the theory, it's the theory that has to change. Every major discovery from the Cosmos Webb survey and other Webb programs has thrown the established timeline of cosmic evolution into disarray. The evidence now points to a universe that assembled itself far more rapidly than expected. Galaxies grew massive, black holes seeded themselves, and star formation shut down at a pace that leaves current models scrambling for answers. According to theorists like Brant Robertson, the physical processes that regulate galaxy growth, known as feedback, must be far more efficient than we ever imagined. The early massive galaxies Webb is finding suggests that the dark matter halos they live in must also have assembled more quickly, challenging our understanding of the universe's fundamental structure. And for all its incredible scale, the Cosmos Webb survey covers only a tiny fraction of the sky. What other surprises are hiding out there? Every answer from Webb raises a dozen new, more profound questions. How did stable galactic disks form so quickly? What mechanism quenched star formation so early? The game has completely changed. We are living in the first moments of a revolution. The James Webb Space Telescope has shown us that the universe is not just larger than we thought, but stranger, more complex, and was built far faster than we ever dared to imagine. The Hubble Ultra Deep Field was a postcard from the past, but Cosmos Webb is the first draft of a new history, one that we are only just beginning to read. The real frontier isn't just about distance anymore, it's about how quickly we can rethink everything we thought we knew. If these cosmic revelations expanded your mind, don't forget to like, subscribe, and hit the bell icon. Until next time, keep looking up. Thanks for watching Sci and Why.